Okay, so this is of Unit 6. Now, you'll need to get the paper out. It looks like this, that you're printing off. And you're going to cut out these 5 different things. Okay, so go ahead and do that. And keep in mind with this unit that, this part, I know you guys don't like watching videos, but it's the introduction to integrals. And it's super important that you understand the basics of how this works. So, excuse me. So it's really important that you're following along, really important that everything makes sense, that you're looking at the notation. I don't think you're going to find it particularly difficult, but we do have to, I'm trying to change this light around, we do have to be able to make sure that we understand it. Okay, so you'll probably, so this is Unit 6, Integration and Accumulation of Change. And what we're doing is we're going to look at the second big topic in calculus. So the first big one is finding the equation of a tangent line. And we'll go back and we'll be reviewing that as well. And the second topic, it has limits in it. So it's a good thing if you've reviewed the limits already. Okay, so basically the second big topic here is finding the area under a curve. Okay, and that area is bounded by a graph, the x-axis, and 2 x values. And we've kind of seen this a little bit when we were looking at velocity before. So we're going to kind of try to tie it all together. So let's say that we're given this graph, and that this is a velocity graph. So we'll call it f prime of x, or v of x, whatever we want. But we're trying to find how far did the object travel between 2 and 10 seconds. So between here and here. Okay, so this part was still a little iffy for a lot of kids when we were doing this. And so I want you to think about how a velocity graph works. So notice that we have meters per second, and down here we have seconds. So if we want to find the distance that it traveled, we would actually look at the area under this graph. Okay, so let's see. It went from 2 to 10. So I want you guys to use a colored pencil or a highlighter or something to show what we're doing. This was the most missed question that we had when we were working with objects in motion, and we're going to those are all going to come back. We're going to work with them a lot. We're going to work with some new notation. Okay, so people are having some trouble. They were trying to find like the velocity at a certain point, but what you need to do is you need to find the area underneath here. Now, you might be thinking, I don't get, what does that have to do with it? So I want you to think about this little rectangle right here. Okay, this is in seconds, and this is in meters per second. So that's kind of the thing. That's what we're not rate over here. So I want you to think, how long is it? It's 8. From here to here is, so the area, and we have second times second. That cancels out, and we get 64 meters. Okay, and remember that would be, we're using f of x, the position function. So we're going to see that we need some new notation. We can't just have graphs like this and then go backwards. So let's kind of look at, what are we talking? And when we're talking about the area under a graph, we're looking at what's called an integral. Okay, so before we had no notation for it. We just kind of looked at it like this and generally thought about what was going on. Okay, so that's how far it traveled. Now, let's look at the same graph, and let's say I want to know how many meters did the object travel during the first 16 seconds? Now, we just kind of wrote it like this before when we saw it. But there is like a notation, and we'll just go kind of really informally right now. Kind of looks like that. Kind of. Okay, but let's just get the general idea. So during the first 16 seconds, it's telling us we're going from 0 to 16. This says find the area under the graph of f of x. Okay, so we're going to take this graph right up here and we're going to break it up into parts. And we've done this before. So I could find this area right here. And that would give me how far the object traveled in the first 2 seconds. I've already got this area right here. I could add in this area right here. Okay, so I'm getting all these little pieces, and then this area right here. Now you're going to see that once we formalize this in calculus, we're going to have a little formula for this, and the formula can look a little bit intimidating, but if you are always thinking about this little picture and how we did this, the formula is not going to be that bad. Okay, so again, I want you to think. We're going to take a triangle, and we're going to add in the rectangle, okay, and then we're going to add in the trapezoid. Now we're going to be using a lot of trapezoids, so I want you to make sure that you remember the formula for area of a trapezoid. We don't want to break this down into a triangle plus a rectangle. Okay, and then the area of that little square. Okay, so again, I want you to have this like little visual that that's all we're doing. We're finding these, oh man, you guys can't even see that. We're finding these little areas all put together. Okay, so this guy is a triangle, so I got to go 1/2 base times height. Okay, this is just a, I guess it was a square as well, right? It was 8 times 8. Okay, now when you want to find the area of a trapezoid is 1/2 base 1 plus base 2 divided by the height. Okay, so I'm going to go 1/2 base 1 and base 2. Okay, so let me get out a piece of paper here. Let's remember this formula because it's been a little while. Okay, so here's base 1, here's base 2. It does not matter which one you call base 1 and which one you call base 2. The height is the piece perpendicular to the bases. So when you're finding the area, which we're going to do a lot of trapezoids, it's really like the area of a triangle, except you have 2 bases. So base 1 plus base 2 times the height. Okay? Now, you're going to see on a lot of the trapezoids that we're going to be working on that they're not in this position, that they are in a position that looks like this. Okay, so when they're in this position right here, we can say, it doesn't, like I said, it doesn't matter which one's base 1 and which one's base 2, and the height is right here because it's perpendicular to those 2 bases. Okay, so ours are going to look like this. We're used to ones that look like this. Okay, so now I'm going back to this guy right here. Okay, so I've got 1/2. The bases, well, let's see, base 1 is 4, base 2 is 8. And the height of the trapezoid, remember it's sitting on its side, its height is 2. Okay, and then again we have 4 times 4. And we can add all those together. So let's see, this is 8 plus 64. See, those will cancel. Plus 12 plus 16. Let's see, 28, 36 is 64. Like about 100. 8, 64, 12, and 16. Okay, did I say 100? Okay, so check my math just in case I made any mistakes there. Okay, so that would be the answer to this right over here. Okay, so that's the first important part of these, and I gave you an example just using a Riemann sum. Okay, so let's look at the next little part. Let's say that, what if the velocity function was not one we could find the area under? So this was really easy because we had a triangle, we had a square, a trapezoid, a square, but what if we couldn't find it that easy? So what if we just had some like really weird shape? Okay, so what we do in calculus is we're going to estimate the area using rectangles. And we're going to use other things as well, but for today we're just going to look at, we can estimate the area this light in here is driving me crazy. Let me see if I turn that off. I think that's better. Okay, so this is a huge part of calculus, is, well, what if we just took some rectangles and we measured it that way? Okay, so let's look at an example. Let's say I want you to find the area under the curve. Of y equals x squared from 0 to 4 using 4 rectangles. Okay, now all of these things are going to be important. Where do we stop, or where do we start? Where do we stop? And and how many rectangles are we going to be using? Okay, so that's something that we have to really pay attention to. Okay, so you want to grab one of these graphs right here. So this is the graph of y equals x squared, and we want to know what is the area from 0 to 4. Okay, and we're going to use 4 rectangles. Now, a problem that we have is, well, what kind of rectangles, where should we put these rectangles? Okay, so in this one, we're going to use 4 right-hand rectangles. Okay, so we're going to see that we either will use left hand, right hand, or midpoint. And we kind of did this at the very, very beginning of the year. Okay, so this is what you do. So if it's a right hand one, you don't start at 0, you go all the way over here to the right. So we're going to start at 1. And I'm going to go right up to that. And then I'm going to try to make this parallel to this right here, or perpendicular to that line. Okay, I'm going to go over to 2. I'm going to come up to the graph, draw that over, and there's going to be my other rectangle. Okay, from 3, I'm going to go up to the graph, go to the left, there's the other rectangle, and from 4, I'm going to go up to the graph, okay, now I want you to make sure that you draw in these rectangles, okay, don't just draw the tops of them. Okay, so here are my 4 rectangles, and it was nice and easy because they happen to each be 1, the width was 1 of each of those. Okay, so I have a magically colored one here of what that looks like. Okay, so on the next video, we'll finish this up.